Hi. So here are all the people who came to my presentation. So let's get started. Okay, so my project this semester was the Mars Moon Habitation Project that I spent most of this semester working on. So my name is Eli Rosam, and I'm going to tell you about my project and my mentorship. So this is Ms. Bordelon and I in the Maker Lab here at the library. We spent quite a while in this lab and had a lot of fun. It didn't always work out, and we ended up doing a lot of the printing using Ms. Bordelon's 3D printer at home. So a lot of the printing was done by her, and I want to thank you a lot for that. And there we go. So I have a Weebly website. This is my portfolio. Basically, it's going to have all the information that we need, and also we need to go to the website. So the website, yay. Here's my first project. So you can see. Wonderful.
It just may be slow with the connection. You get a picture of the...
Maybe it's because...
Okay. There you go. That's probably just slow. It is. That's pretty cool. We like the name of your website.
It's not working. That's what's happening. Okay.
And you can just turn it around and show it to us on your screen.
I think there's 2 monitors.
There it goes.
It's showing.
Okay, that should... Yay! Okay, so here's my website.
That's just slow with the connection.
Yeah.
It's just a slow connection.
So, here's my homepage. We've got that picture here, along with a short little blurb about who Joanna Bordelon is. I also have a notes and a timeline page that were there. So this is my product introduction and purpose paper, where I basically wrote a 2.5-page paper-ish about what I wanted to, what I wanted my project to be, and I was setting my goals for my project on this day. This was back in mid-October-ish. We had already begun on my project back then, and so we had been working on this paper for a while at that point. Here are my journal entries, where I wrote about my experience at this mentorship and my progress on my project, as well as an interview assignment in which I interviewed Mrs. Bordelon and wrote an essay based on her answers, and a little bit about how they pertain to me. We have my resume, my midterm presentation, which this is supposed to be an outline. I wrote a speech. The PowerPoint that I used. So, the invitation to my final project and presentation, my senior expo, which all of you guys are invited, or my invitation for my for this for my final presentation, my final speech, which I haven't uploaded. I'm going to upload that at the end. My PowerPoint presentation is also going to be uploaded at the end, and as well as my product. And then my senior, I don't know what this is. My ISM Expo, I'm also going to put my invitation up there. So that is my online portfolio. Let's go back to this. Great. So I'm first going to talk about my interview for this. Not my interview, my mentorship, and what I did during my mentorship and the research that I did for my project, and then the project itself. So, mentorship breaks down into three main parts: the hours and location, the process, and then the ultimate goal that we had. So, our hours and location, we met here in one of these study rooms, just down the hall from us, and we spent several hours, usually 2 to 5, working on research and outlining the goals for this project. And then we also spent some days in the Maker Lab where we were printing or trying to print and doing more research in the more physical side of things. Is this physically possible? Those kinds of things. Okay. So when I first contacted Mrs. Bordelon, we agreed to meet like the last week of August, second to last week, right around the end of August, at the beginning of school. The official mentorship on the school side of things began in September, so I had a 2 or 3 week head start on all the other students, which I'm really grateful for, because it gave me time to plan and prepare for my project a lot more than I had, a lot more than the other students had. So we met in August. We started talking about the project and outlining it, and Mrs. Bordelon gave me a couple of references for research, which were infinitely helpful, and I was able to spend time working on that outside of the official hours that we met here, and gain extra time and have a better understanding of what I was doing outside of this mentorship officially. And then around mid-September-ish, we began working with SketchUp. We first tried Tinkercad, which is a 3D modeling program that I did not like. I struggled with it. So Mrs. Bordelon introduced me to SketchUp, which works a lot better in my opinion. And it's also a 3D modeling program that I will show you a little bit about in a minute. So I designed the habitat, which is my product, this, and I'll describe more about it, and I did that in SketchUp, so that's fun. This is the home page of SketchUp, or the opening page of SketchUp. You get there and then you click SketchUp free, and this is where you go and you click start modeling. So it's a free 3D designing software, and I was able to have a lot of fun using that and learn a lot about how to design in SketchUp and how to work it, because I struggled with that at first. So I can take you to what the home page looks like, except it's going to do that again, isn't it? Okay. That's my background. That's not supposed to be up. Okay, I'll do that later if I can get it to work later on. So the goal of my project was to design a habitat that can house up to 4 astronauts for long periods of time, 6 months to a year about. And we designed it, and it would be built using in situ resources, the regolith and the materials that we could find on Mars, and build it up from there. So I also planned a virtual reality tour, which is here. I'm going to get to that in a minute. So ISRU is in situ resource utilization, and it's where you use the resources that are around you to make a thing. So for the purpose of this project, we'd be using Martian or moon regolith, which is dusty dirt kind of stuff that doesn't have any of the organic materials that Earth soil does. So it's considered regolith and not soil. And it's fine, it's little particles, and it can be pebbles or sand. So we'd be using that. And we'd have to mix the regolith with a polymer, because the regolith by itself isn't going to make a brick. So the polymer would hold it together in that brick shape or dome shape, or however we end up, whatever shape you end up using, in which case we're doing a dome. And the polymer would both block the solar radiation, which is one of the many problems that you'd encounter on Mars or the Moon, and it would hold it together so that you have a habitable area in which humans can live. So we had a couple difficulties when we were doing the project. When we tried to print here, there were some things went wrong. Sometimes the printer wasn't working, sometimes we were behind. So Ms. Bordelon offered to print at home, which ended up working a lot better, as I was able to send her the files as I completed them so that she could print them. I also struggled with finding out how to curve the walls, which Ms. Bordelon figured out how to do, and then she did it. So I want to thank her for that as well. And then there were a couple other things where we couldn't figure out what was going on, and we went in and troubleshot and just clicked around and played with it until we could figure out what the problem was, and then we fixed it. So one of the main problems we had to think about was, how do we know that this is going to work? We can do it on Earth using plastic, but how are we going to do it on Mars or on the Moon? It was a question that we had. So you'd have to spend quite a while preparing to do a mission of this extent, where you got people living on another body. So you start off, you've got your people, they all know what they're doing, but there's some factors that you can't take into account on Earth. So prior to the mission, several years prior, a rover would be sent to Mars or the Moon, and it would collect the regolith there and bring it back so that scientists can experiment with the polymer to find out which one is the best at binding the material and which one is the best at blocking solar radiation. Because you want to find a happy medium, a polymer that'll do both, because it's not any use if it only does one. So there's a couple of other problems that come with being on Mars, a lot of which can be fixed with technology, like temperature, air pressure, but the temperature can be regulated using an air conditioner. The air pressure can be regulated as long as it's airtight. You can fill it up with 1 atmosphere of pressure. So my product is this, which was designed in SketchUp. So I first sketched it out on paper, had a couple of ideas on what I wanted to do, and then we went into SketchUp and I started designing. And at first I just drew a floor plan, like the kind I had done on the paper. And then I was like, okay, this is kind of ugly. So I spent some time doing research and figuring out how much space I needed for each room. And then I went into SketchUp and I learned how to use the different tools to make things bigger or smaller and change the dimensions, which was, in the end, one of the biggest problem I encountered that felt like the biggest at the time. So we've managed to overcome that. We still have a few small problems that, as you can see, my numerous failed attempts. But we got it to work, and we had a lot of fun. So this is the virtual reality walkthrough. I started off on the bottom floor by the airlock and basically walked through the entire habitat so that you guys could see how it was working. Here we go. Okay, so as you can see, this is the research area. along with a little area for exercise. The research area is mainly designed to be customizable for the mission. So I have a couple of tables in there and a couple of storage areas that would be capable of being moved around as the scientists and astronauts feel they need it to. This small area in here is the exercise room. With Mars having only a third the gravity of Earth, one of the biggest problems astronauts will encounter is muscle and bone degradation. So they'll need to exercise several hours a day in order to keep their muscles and bones from deteriorating too much. So I put a couple of workout equipment in there. So that's how the astronauts will keep their physical health up. In here, we have the greenhouse and the bathroom. We're going to go into the bathroom first because it's smaller. This is the shower as well as a little locker for shampoo and soap and stuff. And then there's also a toilet. Obviously you need a toilet and a sink for the astronauts. So they have that space. There's only 2 doors in here because doors have mass. You don't want mass, honestly, when you're taking stuff to Mars. So there's 2 doors and everything else is enclosed by curtains. So in here, these trees are actually supports. They're supporting the second floor of the HAB because it's a solid, it's flat, right? And it's going to be printed flat, and things don't print flat and also floating. They don't do that. So the trees are supports, and hanging from the trees are plants. I have pea plants and tomato plants up there. There would be a lot more, but this is enough food to feed 4 people for several months, supplemented by freeze-dried food. And then upstairs is where we have the living quarters. This is what it looks like from the top of the stairs, entering into the main lounge communal area. We also have that. That's area designated for storage because the dome gets too small to comfortably sit or stand. So in here we have 4 chairs, 1 for each astronaut and a table. It's a dining room, lounge area where the astronauts can sit back and be comfortable because they're going to need that. And then we also have the bedrooms, which also have that area that's too short to stand or sit comfortably. So that is designated as storage and also life support in ECLSS systems. Those are the environmental systems aboard the ISS, as well as a small bed close to the ground. So it's kind of a private area, but it's mostly an assigned area for the astronauts to stay in, where they have space to, be alone if they need to. And then in here, we're facing the storage area for the food. This is where they keep the freeze-dried food they bring from Earth, as well as the plants and crops that they grow. So you have, once again, that area in the back, as well as some storage lining the walls so that the astronauts can have as much room as they need for their food. And then we're turning towards the kitchen now, which is also small. It has a microwave, more storage, and in the back corner, the feet are so difficult to move. In the back corner, there's a little area for a hose. When I was doing my research, food was cooked on the ISS by, you take your freeze-dried food, your dried-out food, and you add water to it, hot water or lukewarm water. So I added some areas for that. And then we have the upstairs bathroom, which is, a very minimal bathroom. It's got the toilet and the sink, because that's kind of what you need. and it's too short for a shower. And that's kind of the whole area. So, you know, bright colors and textures on anything I could get them on, because I wanted to allow the astronauts to have the best mental state, and your environment does determine that a little bit, which is also the reason we chose to do the greenhouse the way we did. So I have 2 slides of that. That's the end of my final presentations, or my PowerPoint, and I'd like to thank Ms. Bordelon for being my mentor and guiding me through this. Ms. Colick, who's my teacher, she was great. The library for hosting us this entire time, and all of you for showing up and being here. And then here are my citations for my project. Do I have any questions?
So I enjoyed your walkthrough very
Mhm.
much, and just in general, how large is this whole thing?
Okay, it is 16 feet or 18 feet, including the length of the floors, from the base to the top.
Okay.
And then 42 feet here at the bottom in diameter.
Okay. So it's a pretty decent size.
Yeah, this is smaller, just because it's near the top.
Mm-hmm.
I have a little man for scale if you want to hold it and pass it around, as well as a tree, because, like I said, we had a couple problems, and when we tried to print the trees, they didn't exactly print very well. So,
You mentioned some problems during printing. What were
yes,
some of those?
I'm willing to talk about any of those. So we had a couple of failed attempts, like this one, which is only half a dome. The power went out on this one as it was printing, and the printer stopped. So that brings up the question of what happens if the printer on Mars stops. Does it do this? Does it start back up and continue where it was? Does it try to start over?
And does the new stuff bond very well to the old
Yes,
stuff?
that's another problem that we talked about. The polymer has to be capable of bonding to other dried polymer.
That's a good point.
So that would need to be addressed. Make sure that the printer kind of autosaves where it is, so that if anything goes wrong, solar panels get covered up by dust or something, it can start up again at the point where it left off. We also had some other problems. The most fun one is our scale people didn't always come out right. Some of them are missing heads, some of them are missing limbs. So, yeah, there's a scale person.
You can't print people.
No, you can't print people.
Teeny tiny little
Yes.
people.
So, you know, we had some fun with that. This one, we had printed it. We hadn't seen any problems with it when we were designing it. And then it ended up having, one wall was shorter than the rest. And we figured out because the rest had a sill and that wall did not. It's kind of hard to see from up here, so there you go, you can see it. I'll pass it around for you guys to see if you want. And then any others I will definitely talk about. We've got some fun ones up here, like this one, which is straight up ripped.
How did that rip?
We decided to move the airlock from sitting directly on the floor to up a foot because the inside floor is a foot tall. So with the way it was sitting on the floor outside, it was in the floor inside. So we moved it up a bit, and because of that, it needed support because things don't print floating. So it needed support, and we tried to add support, and it messed up the faces, which meant that parts of the airlock didn't print. It ended up having like holes in it. So originally what we wanted to do was take the old airlock out and put a new airlock in and just super glue it in. So this, right? This is the new airlock that we wanted to add. So while trying to cut out the old airlock, this ripped. And then while printing out the new airlock, it doesn't fit. So that was a fun one. So when printing on Mars, if you're going to do the airlock there, you need to have supports, and it needs to be supported in a way that it won't completely fall apart. These are the supports that we used for the airlock. So they just pop right off. I don't know how well you can see that. But yeah, you're all welcome to hold these if you want. This Kimberly wants to hold them.
And how about the
There you go.
finish?
So the finished one is mostly
You can't
good.
touch the finish.
And if you want to ask any questions about any of them that I don't address, I'm open to talking about them. We have our finished one, which is pretty well done. You know, it's got 4 little astronauts on the side of it because that's how the astronauts are going to get in and out of the HAB. And then materials, as well as anyone who's sick, goes through the airlock. So beds. Yes. So beds.
You should flush them right out there. They get sick.
Beds, chairs, tables, and then people in a sarcophagus, basically. It's something that we looked at. How are you going to get someone out if they're injured or sick and can't get into their own suit to get into a rover or wherever so they can be taken care of?
The sarcophagus suit?
A sarcophagus suit. So if someone's at the point where they can't get into their own suit, what the astronauts do is you still have 3 working, living astronauts. So they go through and they lay the sick or injured astronaut in the sarcophagus suit, which is about 6 feet long, and it closes and forms an airtight area over them so that they can breathe and move around a little. But its main goal is to get them from the HAB to a rover or a ship so that they can be returned to Earth to be taken care of. So one person puts the injured astronaut in the airlock in the sarcophagus suit, and someone else pulls them out on the other side. And then they take the person to their to their destination, and they get taken care of elsewhere. All the astronauts will have basic medical training, obviously, but you can't take care of a broken leg in a habitat the size of a small house.
And you said it, but I probably just didn't comprehend it. You said they're on the outside because, is that like an interface with them going inside,
Okay, so they,
or just for?
the astronauts, the Martian and moon dust is bad for human health. So the workaround that we're using is the suits just don't go inside. The suits stay outside, so they're connected to little mini airlocks on the inside, and the astronauts get into the suits through the backs, which are connected to the HAB, and then they close the backs and they walk away.
Oh.
So, you know, one problem.
So the suits are just stuck on the outside permanent.
Yes, when they're not in use.
That's why.
And then they're backing in and out of it? That's
Right.
kind of cool.
Yeah.
Mm-hmm.
How do you protect your suits?
The
from
suits will be
dust
covered
storms?
by basically a shed. It's not, yeah, it's not airtight, but what it will do is it'll protect the suits from dust storms and high winds or anything that comes along, because you don't want them getting too beat up because they're out in the elements. So there'll be a little shed there, and there'll also be a little shed for the rover. Another problem we encountered was things that sometimes work on small scale and things that sometimes work on big scale, but not both. You can actually see it in the domes, things that work on small scale. You look at the very top of the dome on the inside, and it's like all torn up, ripped up, spaghetti. And that's because at that point the dome got a little too work. It was pushed a little too far at that point, and it began to cave in on itself. But because it's so small and it's printed using the lightweight plastic, it was able to be built without being torn up. On the large scale, that won't work. It will cave in on itself. So how we work around that is we have this central circle area, which will meet the top of the dome and support it from the inside. So if anyone wants another look at the central circle, I'm going to pass that around in a minute. Something that works on the big scale, but not on the small scale, are the tree supports, which I have the bottom floor here. And we have the trees, and they got all messy and ugly, and they didn't print all the way. Because they're so small on this scale, they're like 1 millimeter in width. But on the big scale, they're like, half a foot in width. So that'll print just fine on the big scale. On the small scale, it didn't work. So what we did was we made a new tree that was slightly bigger and fit better. So I'm going to pass that around. Please don't lose the tree. And then we have the second floor, which is actually fine. After 5 or 6 attempts that didn't quite work, it ended up working out just fine in the end. And there's a low person in there for scale.
So would the idea be to build not to build the shell, but to build the whole thing straight up?
Yes, so you
and
build
then-
the first
then
floor.
The supports would be there.
Mhm.
Okay.
Yeah, you build the first floor, and then you start with the central dome, and you build the walls and the trees. And then you build the second floor, supported by the trees, and the dome in the central circle continues up and forms the bows out so it can support the dome, and then you print the dome around that.
Makes sense.
Mm-hmm. Yeah. So we had one more major problem with these. When printing the walls, we had them do this.
The walls in here?
Yeah, this is a wall. This is the second
Looks like a
floor.
wall.
It's supposed to be a wall, it's not. So what happened here was we had stub walls. And some of the walls had stub walls, which connected to the sills very well and stayed on, like these two here, right? Well, that just broke again. And then we had some walls that didn't have a stub wall and tend to do this and fling around and stuff. So there's actually 4 walls in my hand that have broken off from the sill. So the ones that didn't have stub walls ended up not working out very well. So we had to go back and consider that and build new stub walls for the floors. And it happened on both the second floor and the first floor. Here's the first floor wall. It's supposed to connect right there to form the second wall of the bathroom, because the bathroom needs walls. And that didn't happen.
So how did you solve that problem?
We built the stub walls. We pulled them out and we connected them very strongly to the sills. Where we had believed they were connected before, they weren't. They were just ever so slightly disconnected, and that ended up causing problems when we tried to print. Oh, here's the rest of that broken wall. That's the second floor. And then there's 5, 6 people. That person is 6 foot tall.
Or 22 millimeters.
So your astronauts don't have to be teeny tiny.
No. Yeah.
7
So-
foot 1, right?
Yeah. So the second floor had a lot of storage space because there were areas that were too small for a person to stand or sit comfortably. But I went to the effort to make sure and double check everything was at an appropriate height for an astronaut to sit. The toilet on the second floor isn't too tall or too close to the dome so that a person can't stand up or sit down. The bedrooms, the heads are facing towards the door so that you have more room when you stand up. So those kinds of things. All that was taken into account. So yeah, do you have anyone else have any questions? No?
I think for me, you covered most of mine already.
You're good?
Okay. All right. I would like to thank Ms. Bordelon again with a card. Can I have the card, please? Thank you. I have to do this in front of the camera so that we can have proof I did it. So here's the card. Here you go. So I think that concludes it. We have cheese and brownies and plates, so help yourself if you want it.
Good job.
Thank you for coming.